Okay, coming up to the end here. Question 9, what mass of copper sulfate pentahydrate, CuSO4.5H2O, is needed to make 200 milliliters of a 0.65 molar solution? So we want to know the mass, so we're going to need to work out the molar mass of the copper sulfate pentahydrate. Copper has an atomic mass of 63.546 units. Sulfur is 32.06. Then there are 4 oxygens, 4 times 15.999 units. And then there are 5 waters. The 5H2O is part of the formula, so we need to include the mass of those waters in our calculation. And then water is H2O, so there's twice hydrogen, 1.008, and then plus another oxygen, 15.999. And adding all this together, we get a molar mass for copper sulfate pentahydrate of 249.677 units, or in other words, 249.677 grams per mole, or 1 mole of the compound has a mass of 249.677 grams. Okay, so we're going to need to know that, and then we're also going to need to incorporate the concentration of the solution. 0.65 molar means that 1 liter of solution contains 0.65 moles of the solute, and then we are going to have to be a little careful here. The concentration has volume units of liters, but in the problem we were given milliliters, so we just have to watch out and make sure that we reconcile those when we're doing the calculation. So let's go ahead and do this. 200 milliliters. We'll first convert from milliliters to liters. There are 1,000 milliliters in 1 liter, so the milliliters will then cancel. Then to go from liters to moles, we can use our concentration. In this case, 1 liter of solution is 0.65 moles of our solute. The liters will cancel. Then we'll go from moles to grams, and we found that 1 mole of our solute has a mass of 249.677 grams. So the moles will then cancel, and we find that we get 32.4580 grams of the copper sulfate pentahydrate. And then finally, rounding off to an appropriate degree of precision, we have 3 significant figures here, 2 significant figures here, 6 significant figures there. All the other numbers are exact, so our answer should have 2 significant figures of precision, and we'll round it off to 32 grams. Okay, so problem 10. If 80.0 milliliters of water is added to 20.0 milliliters of a 0.50 molar solution of potassium iodide, what is the molarity of the resulting solution? So we're starting with 20 milliliters of 0.50 molar potassium iodide, and then we're adding to this 80 milliliters of water. And so what we're going to end up with is 100 milliliters of a more dilute solution with an unknown concentration, and so we want to work out the concentration of that more dilute solution that we made. And so since the number of moles of potassium iodide in the solution is the same before and after, we can use the relationship M1V1 equals M2V2. In other words, the concentration that we start with times the volume of solution we start with will equal the concentration that we end up with times the volume that we end up with. And so our starting concentration was 0.50 molar, our starting volume was 20 milliliters. Our ending concentration we don't know yet, and our ending volume was 100.0 milliliters. So putting those numbers in, and then we want to solve for M2, and doing so gives us 0.1000 molar. And then to round off, we have 2 significant figures here, 3 significant figures here, 4 significant figures here. So the least precision amongst those is the 2 significant figures. So we'll round off our answer to 2 significant figures, and we get that the final concentration was 0.10 molar. Okay, So that wrapped up the main part of the exam, and there was an extra credit problem that was concerned with vibranium, which is a fictional metal that appears in comic books and movies. And if vibranium were a real element with an atomic number of 120, we're asked A, what do you think its atomic symbol would be? B, where would you expect vibranium to appear in the periodic table? And C, if vibranium were to react with oxygen, predict the formula of the compound it would form and briefly explain your reasoning. Okay, now I'm going to need a little bit of space here, so I'm just going to shrink the problem into the corner and bring up our periodic table. So as far as the atomic symbol for vibranium, well, the first choice would be V, except V is already taken for vanadium. And really, there's no rules as to what an atomic symbol has to be. Standard practice is that the atomic symbol starts with the same letter as the atomic name. There are certain historical exceptions to that, but all the elements that have been named recently have followed that pattern. So we should probably start our symbol with a V and then have a second letter that helps or that shows up in or that helps to indicate that it's vibranium. And I've seen a number of good ideas. You could use VB or VI or VR. Now, if you wanted to get to try to get really sneaky, you could suggest an atomic symbol of UBN, which would be the systematic symbol, or that would be the symbol for the systematic name of an element which has not been formally named yet. And the systematic name for element 120 would be unbinilium for 120. And the symbol for that would be UBN. That's a pretty sneaky answer. And I'm going to actually out-sneaky you on this. And I'm going to point out that if UBN were the atomic symbol, then the atomic name would be unbinilium. And we're given here that the name is actually vibranium. And so I suppose if you want to be extra technical, if vibranium were the accepted name for the element, then UBN wouldn't be the symbol. But nevertheless, that is a very clever answer. Going on to part B, where would we expect vibranium to appear in the periodic table? Well, so if it's element 120, then it would probably, well, it would be two elements beyond the last element, the last known element, which is element 118, organoson, and copying the noble gases over to just remind ourselves of where things are. So organoson is at the end of period 7 of the periodic table, and so it would be followed by element 119 at the beginning of period 8, and then 120 would be after that. And so assuming that the pattern of the periodic table continues, we would expect element 120 to be underneath radium in the alkaline earths on the periodic table. And then as far as the formula of a compound that this would form with oxygen, well, vibranium is a metal. We're told that it's a metal, and it's also in the metals region of the periodic table. And oxygen is a nonmetal, of course. Oxygen tends to form 2- ions. If vibranium follows the patterns of the elements above it in the periodic table, it would probably form a 2+ ion. And then since oxygen tends to form 2- ions, you'd end up with equal numbers of vibranium and oxygen ions in the compound. And so the formula that we would expect is VBO. And that is it for that.